All right. Can I start, or do we need to wait for various distinguished guests and visitors? Can I begin? Who's in charge? Are you in charge? Okay, so last time, we discussed the Wiener-Ikehara-Tauberian theorem. Today, I want to discuss applications and extensions of the Tauberian theorem. So for first thing, let's recall the Tauberian theorem. So we proved the following theorem. Let A sub n be a sequence of non-negative numbers. Let f of s be the Dirichlet series an over n to the s, absolutely convergent. Well, absolutely convergent for real part s strictly bigger than 1. Suppose f of s extends analytically to real part of s greater than or equal to 1, except at s equals 1. Where it has a simple pole with residue 1. Okay, these are the hypotheses. Then the conclusion is summation n less than x a sub n equals x plus little o of x as x tends to infinity. So this is what we have. This is the theorem we proved last time. So let's try to make a few remarks and try to relax and extend these things a little bit more so that we can apply this in a larger context. First, it looks like the restriction on s equals 1, that's essentially arbitrary. You can always do a shift translation, so s equals 1 is not a big deal, okay? So minor change, s equals 2 or s equals some c, it doesn't really matter. You can modify it accordingly, so that's not a problem. The, the residue here, what if the residue is r? So let's modifications. So remarks. If the residue is r, positive, then we may consider f of s equal to summation an over r over n to the s. Right? And then that series now has residue 1, has a simple polar residue 1, and apply and thus we deduce summation n less than x, a sub n equals Rx plus little o of x. So in general, if the residues are, this is the kind of formula you're going to get. Second, what happens if the residue is 0? If the residue is 0, that means there's no pole, but let's see if this works. Then we can consider f of s plus zeta of s. Okay? We can consider f of s plus zeta of s. ANs are still non-negative. Zeta of s is, okay, this has a pole, simple pole at s equals 1. And now the residue here is 0, the residue here is 1, has a simple pole, residue 1. And so we can apply the Tauberian theorem to this, and you end up getting summation n less than x, a sub n plus 1 equals x plus little o of x, right? Oops, little o of x, right? And therefore, you get rid of that thing, yeah? So, implies, oops. If the residue is 0, this thing is still valid. Okay, so this is valid for no matter what. So this is first reduction. Second reduction, modification is what to do with respect to, okay, I hope you have this kind of memorized. Okay, I'll rub this off. So we'll now modify the Tauberian theorem to prove the following theorem. Suppose G of s is a Dirichlet series. This time B sub n's are real, but they're not necessarily positive. And if real, suppose that G of s is a Dirichlet series absolutely convergent for real part s bigger than 1. Okay? Suppose it admits if G of s extends analytically to real part s greater than or equal to 1 except at s equals 1 with a simple pole at s equals 1 with residue little r. Okay, and further suppose I would have liked to stop here, but I just need to make one more small additional hypothesis. Further suppose there exists a sub n's, real, non-negative, satisfying the hypothesis of the Tauberian theorem, the original one. What is it? satisfying, further suppose that there are these numbers with b sub n bounded by a sub n. Okay, so I just need this extra. You give me any other series with real coefficients, but if I can dominate it by something that satisfies the original Tauberian theorem, then I can actually conclude what I want. Then summation n less than x b sub n is equal to Rx plus little o of x as x tends to infinity. Okay. Now in practice, if you have a Dirichlet series with real coefficients, in practice you can always find this a sub n's and work this through. It will always happen. Okay? So how do you prove this? The proof is easy. Apply the Tauberian theorem. To g of s, f of s minus g of s. F of s minus g of s is a Dirichlet series whose coefficients are a n minus b n, which are non-negative now because of this hypothesis. And you can deduce the result from that. Okay? Now, sometimes people put a constant here, and of course that's no big deal. So okay, it's as long as it's dominated by some fixed constant times a sub n, it's still okay. So to deduce the result. So this is the third point. So this is remarks. I'm trying to extend the range of applicability to slightly more general situations. Now, so far we've got bn's real. Now I'd like to make b sub n's complex numbers. So I'd like to allow for that possibility. It would be nice to have that kind of theorem. So how do you do that? No. The residue will be capital R. So f of s satisfies the original Tauberian conditions. It has a residue capital R. G of s has a residue little r. Therefore, this silly thing has residue R, capital R minus little r, right? Apply the theorem, get the theorem, and you get summation an minus bn, n less than x, equals r minus little r x plus little o of x. Correct? And now you know the summation an is r, so you subtract, and you get the, okay, so that's that, okay. Now, okay, as I said, I want to relax this condition to b sub n's complex numbers. So number 4, want to relax bn real to bn complex numbers. And in order to do that, you need to do a little bit of an exercise, which I will leave because it's actually can be done in your head. If f of s is analytic, in real part s greater than or equal to 1, then so is f of s bar, okay, as a function of s. Okay, so you can do that. Analytic means complex differentiability. So all you have to do is prove the silly derivative exists, and you can do that. Okay. Now, what happens in the context of Dirichlet series? If I have, let's use G. Let's use G of S. Because I want now G of S to be complex numbers. If I look at G of S bar, right, that's the series. Okay, and now if I take a bar, that's a bar, and the n to the S bar bar is bar. Gone, right? So you can figure that out. So the advantage of looking at G of S bar bar is that I've conjugated the coefficients. Okay, so if I would like to change this thing into complex numbers. If I do that, and let's suppose I want to now say this theorem is still valid. So it extends analytically, except for a simple pole residue R. Suppose there are these ANs which are non-negative that satisfy this in the usual fashion. And then I'm going to assert this. And how do you assert that? Well, you just, I'm going to leave this as a kind of an exercise for you to do. It's very pretty routine. The idea is you look at, let's call this G star of S. Okay, let's call that G. So give me G of S like this. G star will be the one with the complex conjugates. Then G of S can be written as G of S plus G star of S plus I times G of S minus G star of S over 2. Is that correct? Something like that. Let's see. If I have the 2, this is the Bn plus Bn bar divided by 2, that's the real part. Bn minus Bn bar is the imaginary part. Oh, so there's no I here. That's it, yeah. Okay. So you can write your G of S as these guys. Okay. Now there's an I in these coefficients. These are purely real. These are purely imaginary. Now I think I'll leave it to your imagination to figure this out, okay? So dot, dot, dot. You can now apply the theorem and deduce the result very cleanly. So there's no real constraint, yes?
So if you have like counter number of poles on the rightmost line, so do the same thing hold instead of one pole?
No, no. This only works with one pole. This only works with one pole, yeah. But there are techniques of removing those poles that you can, but this is, as I said, it's an introductory course, an introduction to the book. I mean, she asked me for an introduction to the book on analytic number theory, so I'm just kind of giving you a crash course so you can read the book on your own. Yeah. All right, so does that okay with everybody? Now, there is a good point to your other question, that is, supposing I had not a simple pole, but a double order pole or a triple order pole, high order poles, and the question is, can I deal with it? And interestingly enough, you can actually use the Tauberian Theorem to deal with higher order poles, but I'll show you that trick maybe by end of today's lecture. Okay? But you need to do a trick. So let's try. We're going to try to apply this theorem now for some interesting questions. So first application is so let's have some applications. Well, we already applied it to get the prime number theorem last time. Applications. So problem is to count squareful numbers. So a natural number is called squareful if p divides n implies p squared divides n for all primes p. In other words, when I factorize the number as a product of prime powers, all the powers are 2 or more. So for example, 12 is not squareful. Because it's 2 squared times 3, and 3 does not appear to a power 2 or more. Whereas, squares, cubes, and so on and so forth, 2 squared times 3 cubed, 2 cubed times 3 squared, let's say, is powerful. So the problem is count the number of squareful, okay, in the literature both these terms are used, so I have a tendency to, squareful, powerful, they're both the same words, okay? So count the number of squareful numbers. So let's define a sub n to be 1 if n is squareful and 0 otherwise. Okay? And now try to consider the Dirichlet series an over n to the s. We'd like to consider that Dirichlet series, and what we'd like to do is get our hands on summation a sub n, because a sub n is 1 whenever n is squareful and 0 otherwise, therefore we would like to get our hands on summation a sub n. So the question is, what is this Dirichlet series? Now, interestingly enough, the squareful property is the function a sub n is a multiplicative function, in the sense that if n is squareful and m is squareful and n and m are relatively prime, then n times m is also squareful. That's clear, right? Okay, so this is a multiplicative function. Therefore, it neatly factors into a big Euler product. It's a multiplicative function after all, remember? We talked about Euler products, the zeta function, right? Right? Now, p is not a squareful number, therefore this term doesn't exist, right? It's 0. But that's squareful, everybody else is squareful, so this whole Euler product, p, is really 1 plus 1 over p to the 2s plus 1 over p to the 3s, so on and so forth, right? That's what it is. Okay. So I think we can kind of sum that. So how do we sum this? 1 over 1 p to the 2s. Oops. I think you can all do this. So it's this thing is a geometric series from here onwards, right? So from here onwards, I have 1 plus 1 over p to the s plus 1 over p to the 2s, right? Dot, dot, dot. Fair enough? So that's 1 over 1 plus p P to the 2s, and yeah, 1 over P to the s, right? Get something like that. Which can be simplified even further. It's 1 plus 1 over P to the s, P to the s minus 1. Okay. So that's the Euler factor, looks like this. Now let's just look at let's just look at let's see, zeta 2s well, let's see. So one of the, okay, let me explain to you the philosophy behind trying to understand this factor. You could see that this is pretty much close to, P to the s. So the philosophy is, this is looks like 1 plus 1 over P to the 2s. Looks like that. And 1 plus 1 over P to the 2s, you try to factor as much as possible out of the picture. So you could do the following. So just write it, you think it's that as the approximation for that, but then you just make sure you get rid of it. Put this out. So let's put this out. So keep this. So put this out here. And try to understand what this Euler these two look like. So it's 1 plus 1 over P to the s, P to the s minus 1 times this one, which is, well, P to the 2s here over P to the 2s plus 1. P to the 2s plus 1 inverse, okay? So you get something like that. So let's try to simplify this a little bit. This is going to be P to the s, P to the s minus 1. So that's P to the 2s minus P to the s plus 1. I think I might have actually complicated this a little bit. Yeah, I think there's a slightly easier way to do this. Let's just look at this factor alone, because that's the Euler factor anyway. So let's look at that. That's P to the 2s minus P to the s plus 1 divided by P to the s minus 1. So what I'll try and do is I recognize the numerator. See, remember x squared minus x plus 1 is equal to what? Is equal to x cubed plus 1 divided by x plus 1. Is that correct? Let's see. Is that right? Does that look okay to you? X cubed minus x cubed. Right. Okay. So is that right? Okay. If that's okay, then what we will do here on the numerator is factor this as P to the 3s plus 1 over p to the s plus 1, right? And then put 1 over p to the s minus 1. Fair enough? Everybody okay with this? Okay. Then, okay, so I think I gave you a bum steer on this one. You could have done it directly, and this is now much cleaner. There's this famous joke with Norbert Wiener's lectures were terrible, but Norman Levinson, who was one of his students, said he learned a lot because the mistakes were instructive. So I'm hoping that's the case here. All right, so now we have this guy. So notice p to the 3s plus 1 over p to the 2s minus 1. Yeah. Did I do this right? I guess. P to the 3s plus 1 over p to the s plus 1. That's the numerator, and then I kept it. Okay, that's good. So this is that, and then there's got to be 1 over p to the s. Is that correct? Okay. All right. So now the idea is to divide, to do the following, to divide. So this thing can be thought of as p to the 3s plus 1 over p to the 3s divided by p to the 2s minus 1 over p to the 2s. Okay, so I just rewrote that silly 1 over p. The advantage of doing that is the Euler factor now becomes 1 over p to the 3s times 1 minus 1 over p to the 2s inverse. Exactly. Good. So let's call this Dirichlet series f of s here. Try to understand the series. So you're confronted with a problem of counting certain numbers. You concoct a Dirichlet series. You try to understand that Dirichlet series, and you want to put it into a position where you can apply the Tauberian theorem. Okay? So this f of s now has been neatly factored as a product over primes, 1 plus 1 over p to the 3s, 1 minus 1 over p to the 2s inverse. Okay? Now, recall zeta of s, the Riemann zeta function, which we all now know something about, is 1 over 1 minus p to the s inverse. So I recognize the second factor as zeta 2s. So I can remove that from the picture. Right? Now, keep in mind that x to the 6 minus 1 divided by x cubed minus 1 is x cubed plus 1, correct? Okay. So I recognize this as 1 plus x cubed, and I rewrite that as zeta 2s times product p. Well, it's 1 plus, sorry, if you don't mind, I will write this identity as 1 minus x to the 6 over 1 minus x cubed as 1 plus x cubed, so that you can see it. Okay? I'll do it like that. Okay. Then to do that, that would be 1 minus 1 over p to the 6s over 1 minus 1 over p to the 3s. Right? And now I write this now as zeta 2s times product p 1 minus 1 over p to the 3s inverse times 1 minus 1 over p to the 6s without an inverse. And now I recognize this guy as a zeta function. And then this guy as zeta 6s inverse. Right? Therefore, the generating function, the Dirichlet series associated with squareful numbers, is this concoction, which you would have never guessed unless you did it this way, right? So, thus, f of s equals this an over n to the s, n going from 1 to infinity, is actually equal to zeta 2s, zeta 3s over zeta 6s. And we all know about the Riemann zeta function. We analytically continued it for real part of s bigger than 0 with only a simple pole at s equals 1. So zeta 2s has a pole where? S equals a half. You're right, exactly. So this guy's got a pole at a half. This guy's got a pole at a third. This guy's got a pole at a sixth. Or sorry, it has a 0 at a sixth. It's on the denominator, right? It's got a 0 at a sixth. But I don't care. The first guy seems to be a half. So I can assert f of s admits an analytic continuation for a real part of s bigger than or equal to a half, except at s equals a half. Where it has a simple pole with residue equal to what's the residue? Huh? Well, for zeta 2s it's 1. Well, it's not quite 1 actually. So see, zeta s behaves like 1 over s minus 1, correct? So zeta 2s behaves like 2s minus 1, right? And so that's the same as 1/2 of 1 over s minus a half. So zeta 2s behaves like that. Zeta 3s is analytic at a half, so that's like zeta 3/2. And zeta 6s is okay at a half, so that's zeta cubed, zeta 3 rather. So this is going to be 1/2 zeta of 3/2 divided by zeta of 3. That's the residue. Okay? So blindly now we can apply the Tauberian theorem, right? Well, not quite. I mean, you shouldn't, you know, not quite, but practically. So we can just automatically apply the Tauberian theorem and deduce that by the Tauberian theorem shift the thing, right? Before it was s equals 1, therefore it was x to the power 1. Now it's s equals a half, therefore it's x to the power half, okay? So you get an asymptotic formula for the number of squareful numbers by doing this kind of an analysis. Very useful technique to have. Okay, now in the remaining time, I want to give you another application to the study of primes in arithmetic progressions, originally called Dirichlet's theorem. But this theorem has a a long history, which is badly recorded in the Wikipedia article. So if some of you are, computer nerds, please read up Davenport's book, Multiplicative Number Theory, get the history straight and put it in there. It starts in 1837, but Dirichlet had a lot of difficulty in proving that there are infinitely many primes in a given arithmetic progression. And it took him a couple of years to do this. And I think the final proof comes out in 1840, and he did it in a very complicated sort of way. So, and besides, Dirichlet's theorem only gives you infinitely many. It doesn't give you an asymptotic formula. So 1837, Dirichlet proves infinitely many primes in any arithmetic progression A mod Q, with A and Q relatively prime and Q a prime number. And I think he has to work a little hard, and finally in 1840 he gets the whole thing with Q composite. It has to do with Gauss sums, Q composite. Okay. In order to do that, in order to deduce Dirichlet's theorem at one go, we need a little bit of crash course on what is now called character theory, at least for abelian groups. In fact, the whole subject of representation theory, which as we know it, representation theory in mathematics today, begins with this problem. So in trying to solve this problem, Dirichlet stumbled on the important idea of a character. He didn't call it a character. In fact, he wrote down, very concretely what these functions were, but never called them a character. And so, as I say, keep saying, it's not the solution of the problem that we're interested in. It's the methods and the concepts that it unravels. And then perhaps it isolates a new concept that has to be isolated and studied on its own. And that's what happened with this, with respect to Dirichlet's work. So let me try to highlight this a little bit. So you have the integers mod Q, the coprime residue classes, the group of coprime residue classes. A character is a mapping into the non-zero, into the multiplicative group of non-zero complex numbers. It's homomorphism. Homomorphism. Now, sorry, star, yeah. So now, you all know the fundamental theorem of abelian groups, that every abelian group is isomorphic to a direct product of cyclic groups. So essentially, if I'm looking for homomorphisms of this particular abelian group, I can reduce my study to homomorphisms of cyclic groups. So if I had a cyclic group, G cyclic, by the way, these are all finite groups, finite cyclic group, a homomorphism of a cyclic group is easily determined by the following procedure. If take a generator G, fix the generator, and define chi1 of G to be a primitive root of unity. Zeta is a primitive Gth root of unity, right? So fix a primitive Gth root of unity and just define chi1 of G, chi1 on this particular element to be that primitive root of unity. And because it's got to be a homomorphism, all the powers of this thing are now defined. You've defined the whole chi1 on the full group. Okay? So that gives you one character. Okay. And now all the characters, you could have picked a different root of unity. They're all generated by that. So the point is, all the characters now of this particular group are powers of this single character chi1. So in other words, the collection of characters of this cyclic group forms another group which is also cyclic. In fact, isomorphic. There's a kind of canonical isomorphism which we will not get into right now. So if I take this abelian group, I factor it into direct products of cyclic groups, and the character then decomposes into component characters, and I just showed you for each cyclic group there's a character, a group which is isomorphic to the group itself, and therefore the number of characters is equal to the order of the group. Yeah. Now this is kind of in a nutshell the struggle that Dirichlet had because he didn't have these notions, and so I was struggling through. And he actually wrote down characters very explicitly. He didn't call them even characters. Notation is very important in mathematics. Coming up with good notation, like 0, as I explained, is a big deal. It is a big deal. So coming up with good notation to understand what's going on, like here, these are characters, that's what he was playing with, and that he recognized the importance of these objects in order to prove this theorem is an important leap in mathematical thought. So you have these characters, and so we now see that the character group of Z mod QZ star has order phi of Q. Right? It's got order phi of Q. So for each character, which is one of these objects, you can define what is called now LS chi, Dirichlet L function, which would be summation n going from 1 to infinity, chi of n over n to the s, where I interpret chi of n as chi of n mod q. Now, n is not coprime to q, we just set it to 0, which is, so this is, so chi, so understanding that chi of n is 0 if n and q are not relatively prime. Okay, so understanding that. So this is interesting because this is 1837. The Riemann zeta function as a function of a complex variable was introduced in 1860. Dirichlet was still fixated on studying functions of a real variable. Okay, so he defines it as a function of a real variable, really. He doesn't really think of it as a function of a complex variable. Euler had already looked at the zeta function again as a function of a real variable much earlier, although one could argue that he had thought of it as a function of a complex variable too. The point that I think Dirichlet noticed was that this thing has similar properties to the Riemann zeta function because chi is a homomorphism, and small check that you have to check that since chi of n1 times chi of n2 is chi of n1, n2, it's a homomorphism, it's a multiplicative function, exactly. So you can write this as an Euler product as before, completely multiplicative function. So you can write it as an Euler product with a geometric series, and now it's all old hat. The geometric series can be summed, and there you are, right? That's the answer. So it has a nice Euler factor, Euler product, similar to the zeta function, except now I've got this character value stuck there, okay? And Dirichlet notices the following thing. So he introduces these series, and then he wants to understand the analytic properties. Remember the whole, now I'm going to give a modern complex analytic perspective on it. He, without the terminology, without the notation, he was struggling very hard to continue these things and extend them. But we can do it now with relative ease by making a couple of observations. First observation, well, two observations are essential to get this going. These are called the orthogonality relations. So fix A and look at the character sum over all the characters. There are only finitely many, 5q characters, okay? Fix A. So if A is 1, is the residue class 1, 1 is the identity element, so chi of 1 is always 1, so this should be 5q if A is 1 mod q. Okay, and if A is not 1 mod q, okay, this sum turns out to be 0. And how do you prove that? Well, here's how you prove it in one line, but it requires a little bit of work, okay? If A is not congruent to 1 mod q, you look at the group generated by A. Okay, it's a non-trivial group. On that group, we know how to construct characters. So there is a non-trivial character you can construct such that chi 1 of A is not 1. Okay? You construct that. Then there's a simple procedure to extend that character from that subgroup to the full group. So what happens is if I were to to prove the second point, if I multiply by chi 1 of A, the whole sum, where I've chosen chi 1 such a way that chi 1 of A is not 1 because A is not 1, right? So because A is not 1, there exists a non-trivial character such that chi 1 of A is not 1. This sum can be thought of as chi 1 times chi of A. Now, you know, in a group, it's a multiplicative group, as chi ranges over all the characters, so does chi 1 chi. So this is again the same as right? In a group, that's what happens. Therefore, this sum is equal to this sum, but I chose chi 1 of A not to be 1, therefore that sum better be 0. Okay, that's the proof. Okay? Similarly, you can do what is called a dual relation. I mean, it is amazing that because of this problem, Dirichlet stumbled on a very important idea called representation theory. No joke, okay? Much of what I'm saying, of course, in this language was developed by Frobenius and Schur and other people later on, right? The second result that he needs is chi of A. This time I fix chi and I vary over A and Q relatively prime. So vary over the group elements. If chi is the trivial character, so by the way, the trivial character will be denoted as chi 0, trivial character, which is the character that sends everybody to 1. There's always that silly character, right? If it's the trivial character, you're going to get 5q again. If it's the non-trivial character, a similar argument as before shows that this is equal to 0. And the way you do that is, if chi is a non-trivial character, there's got to be a b such that chi of b is not 1. Hit the thing by chi of b, same argument. And now as a runs through all the things, so does ab, and then it has to be 0. Okay, so this is the kind of, these are the very important ideas, but there's a little bit of a proof that's needed in that existence of that particular character that does what you want it to do. Okay, so these are called the orthogonality relations. And once you have them, you're practically in business. So let's see what the second one is saying. So notice 2 implies so I'm looking at all the residue, all the numbers from 1 to q. Okay, when n is not co-prime to q, this is 0 anyway. When n is co-prime to q, I pick up every residue class once. So you're picking up that, and therefore that has got to be 0. So in other words, the partial sum, summation chi n, when up to q is always 0. Okay, so let's try to analyze the Dirichlet L function, L as chi, when chi is not equal to chi naught, and use Abel's technique of partial summation to change the Dirichlet series into an integral. So we know how to do that. You put S of x to be summation n less than x, chi of n, the partial sum. Then this thing becomes S1 to infinity, S of x over x to the s plus 1 dx. Okay? Now, the first, this property here is telling us that every time you hit a complete interval of length q, it's 0. The next interval from q plus 1 to 2q is again a full set of residue classes mod q. It's again 0. Next interval is again 0. So what we can do is take this interval x and split it up into first intervals of length q, and whatever is left over has size at most q. All those intervals of length q, you have 0. What's left over is at most a number of summands is at most q. Therefore, we see that S of x is always bounded by q. You can do better, but we'll not worry about that now. In other words, it's bounded. Now, if it's bounded, this integral converges for real part of s bigger than 0. Yeah. So therefore, we see theorem for chi not equal to chi naught, L as chi as a Dirichlet series converges for real part of s bigger than 0 and defines an analytic function there. In that region, defines an analytic function. Okay, so without any work, actually with some work, I mean this orthogonality is not a joke, but some group theory injected into the picture allows us to deduce that the Dirichlet series actually converges in a larger region, which we didn't know before. Before, all you knew was chi of n was bounded by 1 and converges absolutely for real part s bigger than 1, but it actually converges conditionally for real part of s bigger than 0. Converges absolutely for real part s bigger than 1, but actually is an analytic function for real part s bigger than 0. Okay. Okay. And by the way, for chi equal to chi naught, I should have said something here. For chi equal to chi naught, which is the trivial character, what do we have here? Chi is the trivial character. So when p divides q, this is just 0, it doesn't, so there's nothing there. When p doesn't divide q, it's 1, and therefore that looks like the zeta function, except that you've removed the q, the p Euler factors with p dividing q. So essentially what we have is ls chi naught is equal to the Riemann zeta function with the Euler factors removed. So you have this, and therefore this has a pole at s equals 1, and the residue is whatever it's supposed to be. It's phi of q over q or something. So, which is analytic for real part of s bigger than 0, except at s equals 1, where it has a simple pole with residue phi of q over q, I think. Okay, so basically we know now everything, well, not everything, but enough for the further discussion. At least we now know that these Dirichlet series have analytic continuation to a larger region than we had thought of before. Oops, I'm running out of time, so I better speed up a little bit here. Okay, I'll need this thing, so let me kind of write this. Here. So far so good, right? Now what we'd like to do is we'd like to see if I can get our hands on primes congruent to A mod Q. But let's try to first get our hands on primes congruent to 1 mod Q. So let's look at the following combination. Consider the logarithmic derivative firstly, minus L prime, just like before when we had zeta prime over zeta of s, right? So if we look at L prime s chi over Ls chi, you can see that this is going to be, I'll leave this as an exercise for you to do, chi of n, the von Mangold function over NVS. So it's exercise. So if I did the zeta prime over zeta before, right? Just try to do this and just check that it's actually the case. So what happened now? The zeta prime over zeta, the earlier one, got twisted by this character chi. And what Dirichlet observes, or not this in this elegant style, what he observes is if I take the sum over all the characters chi of, well, let me put the minus sign inside here. Take the sum, put the sum out here, now interchange summation. in the region of absolute convergence, I get this, correct? And keeping in mind that real part of S is bigger than 1, so that everything is absolutely convergent and I'm justified in this interchanges of summations. Keeping in mind that real part of S is bigger than 1. Okay, now, I wish I didn't write so big. Now, what do you have here? You have summation chi of n over all the characters chi. So I use this relation, which tells me that summation chi of A spits out a phi of q whenever A is congruent to 1 mod q and 0 otherwise. So that means this sum is essentially 0 unless n is congruent to 1 mod q. Okay. Let me continue here, because I still need that relation, so this theorem is important. So this becomes summation chi minus L prime L S chi equals summation, well, lambda of n, or n to the s, phi of q, n is congruent to 1 mod q, right? That's what you end up getting. Now, this is a Dirichlet series, non-negative coefficients, has an analytic continuation to real part of S greater than or equal to 1. The left-hand side has a meromorphic, well, certainly has an analytic continuation for real part of S strictly bigger than 1. We need to worry about zeros of the L function on the line real S equals 1. So suppose LS chi is not 0 for all real part of S equal to 1. Okay, for S real part S equals 1. Supposing, so we'll need to assume this. Remember before, in trying to prove the prime number theorem, we needed to assume the Riemann zeta function wasn't 0 on the line real S equals 1. Now we need this for all the Dirichlet characters. We need that, right? So if the denominator is not 0, there's no problem. See, my notation, by the way, I don't know why I've used this notation. So L prime over L S chi, I mean, people write this just for elegance, I suppose, is really the same as L prime of S chi over L S chi. I mean, that's just a notation, okay? It's just elegant notation. Oh, so you have something like this. So this guy here is analytic provided, even for real S equals 1, provided it doesn't vanish. And the character chi naught is really the zeta function, which of course we already studied before, and we know that zeta prime of zeta over zeta has a simple pole at S equals 1 with residue 1. So therefore, if we suppose this, then the Tauberian theorem implies that phi of q summation n less than x lambda of n congruent to 1 mod q is asymptotic to x, because it's a simple pole, residue 1, S equals 1, right? Everybody okay with that? Now, what is this saying? Well, remember this lambda of n is essentially log p when n is a prime power, right? So it's 0 otherwise. So it's only supported on prime powers. So firstly, there are primes in here, primes congruent to 1 mod q, but there are also prime powers, p squareds, p cubed, and so on and so forth. But remember, we agreed last time, a simple count, squares count for at most root x, cubes count for at most x to the 1/3, and so on and so forth. So the contribution from squares, cubes, etc. in this sum is very, very small, exactly. So you may as well replace it as with log p, with p a prime and p congruent to 1 mod q, because the other guys are contributing much less compared to x. So this proves that the number of primes p less than x, p congruent to 1 mod q, is asymptotic to x over 5q. So you have a very nice, this is the generalization of the prime number theorem to the arithmetic progression 1, though, at the moment. We haven't done in general yet. So this is not bad. Of course, this is not Dirichlet's theorem. Dirichlet was only infinitely many. He never got asymptotic formulas because the Tauberian theory, all this stuff comes much later. So I hope this is clear, right? How one gets it just at one go. Once you have the Tauberian theorem in hand, you just have to set up the L functions again, and bingo, you get the result, right? Now the question is, of course, how do I change 1 to A? Okay. Well, this is another stroke of genius from Dirichlet. So what Dirichlet does is he goes back to this line and says, well, before I do that, before I sum this, let me just multiply by chi bar of A and add them up, okay? So that means instead of just adding this up like what I got here, this would now change to chi bar of A chi of n, right? Now chi bar of A is chi A inverse, right? So this is the same as the chi A inverse. So that means this is, and this is a homomorphism. So this is chi n A inverse. And now we go through here again, so I have to multiply by chi bar of A here. And here, it's now whenever this guy is congruent to 1 mod q, which is the same as n congruent to A mod q. Okay, so this is the cute, very cute thing, and now you end up getting this. And it's the same idea. We still need the same result in order to get this combination to be analytic. And then we can apply the Tauberian theorem again. The same contribution is coming from the trivial character, and so you end up getting this for any coprime residue class. So you get it all at one go, right? Okay. So this is essentially the proof of Dirichlet's theorem with this asymptotic formula. The only problem left remaining is this non-vanishing result of the L function on the line real S equals 1. And probably you could guess that it is similar to the little trick of 3 plus 4 cos theta plus cos 2 theta that I used last time. And the answer is it's almost. It almost works. Okay? And there's another thorn on the way. Thorns on the way are actually turn out to be flowers on the way, because a thorn means that you've probably stumbled on an important idea. That's what it means. So, so don't get discouraged if you're stuck in a proof. You've probably stumbled on an important idea. Okay? So so this non-vanishing requires not only that little trigonometric idea that Hadamard, de la Valle-Poussin used in the Riemann zeta function case, but you need one more idea, which is due to Landau, which bypasses the agony that Dirichlet had experienced in his early work in trying to show that L1 chi was not 0, because he was only arguing at S equals 1. But we're going to show everything is not 0 on that line. Okay? So maybe that's enough for the day. Today is what, Wednesday? And so the next lecture is on Friday, and we'll see. We'll take it from there. Okay.